Okay, so I'd like to welcome everyone to the Modern Machining Methods webinar series. Today is part 2, Advancements in Hole Making. So today's session is going to be broken up into 2 different sections. Our first presenter is going to be Kevin Wismer. Kevin is an applications engineer for DP Technology, and he's been with DP for 4 years now, and he's going to be presenting on hole making in Esprit. Following Kevin is going to be Jim Nielsen, who is the round tool specialist. And Jim's been in the industry for almost 40 years now. Most of that has been with Sandvik Coromant. And Jim's going to be presenting on drilling theory, process considerations, and Coro Drill 860. So throughout the presentation, we would encourage you to ask questions using the questions dialog in the GoToWebinar utility. And Freddie Wilson, Sandvik Machine Tool Solution Specialist, has been with Sandvik for 20 years, and him, along with myself, will be answering questions throughout the presentation via the chat dialog. And then at the end of the presentation, we'll also have a live Q&A session where we will be probably going over some of the more frequently asked questions that have transpired throughout the session. And hopefully we'll get to everybody's questions, but if we don't, we will follow up with you individually after the session is over. So I'm going to go ahead and change the presenter to Kevin and get this thing started.
All right, thanks, Dan. Like Dan said, my name is Kevin Wismer. I've been an applications engineer with DP Technology for 4 years now, and I'm going to discuss with you some hole making functions within Esprit. So the basis of hole making in Esprit, show you some tips on how to do that and how to help you make holes more efficiently and give you a clear picture of the advancements in Esprit's hole making ability. So on the screen, you can see the topics that I'm going to be discussing today. So first thing we're going to talk about is going to be hole recognition. And so Esprit offers some tools for hole recognition. So we still have what's called the legacy hole recognition, and it's still available in Esprit 2020. It's our older version of the hole recognition function, but it's still used by some of our customers, so we like to leave it in there. It's limited selection capabilities. You can still filter by max and min diameter and a few other factors, but that's about it. It's still a very effective tool, but we do have a new hole recognition function, or a newer hole recognition function that's a lot more powerful. So the new hole recognition function will be shown on the feature ribbon in the new Esprit, and then also on the bottom there, that's on the features tab in Esprit 20X. You can see it's highlighted there, the hole recognition function. And the way it's used is you select a face or an entire solid model, and it will recognize all of the holes on that face or solid model. You can use different factors to filter your hole selection. So min and max diameter, you can set a range that if a hole falls within that range, it gets recognized, and if a hole falls out of that range, it will be ignored. Minimum hole opening, so a hole has to be completely, or at least complete that degree around. So if it's not more than 180 degrees completely around, then it will get ignored. And then a couple other options there: combined coaxial hole. If there's an interrupted hole, but the holes are still on the same axis, then it'll actually just recognize that as one feature. Propagate hole faces and active work plane only, I'm going to talk about shortly. Split custom hole, if there's a pretty custom hole with a lot of different sections and features, you can actually split that up into different features, which is a nice capability there. And then some grouping options of how you want to actually group all of the holes. So if there's different diameter holes, do you want to group them all in one hole feature or in separate hole features? So you have that capability as well. All right, so two of the big settings within the hole recognition function are going to be propagate hole faces and active work plane only. Propagate hole faces, when turned on, will actually look through the entire hole itself and recognize any sort of counterbore surfaces, countersunk surfaces. It recognizes all these surfaces and inputs that data into the hole feature itself. So if that's not turned on, then it'll just recognize the hole that meets the criteria that's set and not necessarily all of the faces of that hole. active work plane only is used to recognize holes that are only normal to your W vector of the work plane, the active work plane. So if it's turned on, in the first image there, you can see it only recognizes the 2 holes that are actually normal to that blue or W vector of the work plane. If it's turned off and you select the entire model, it'll actually recognize all of the holes around the model and not just the ones that are normal to your active work plane. So another nice thing in Esprit and hole recognition is that you can actually just select a face and then select your drilling operation, and it'll automatically create the feature for you. That hole recognition function is nice because you can filter and kind of reduce the amount of holes that you're going to recognize. But if you just want to select a face and group all of the holes on that face, then you can do that by just selecting the face and going into a drilling operation. I'm going to go ahead and show you that now. So right here, I have a part with some holes on this face, and I'll just go ahead and grab this face here. And typically, if I wanted to use that hole recognition function, I could go to Feature, select my hole recognition function here, and then I can set up all my filters and hit OK, and it'll create that hole feature for me. I'm going to go ahead and delete that one for now. I can also just select the face here, and I'll grab this face too. There's some holes on that face as well, so we have 2 faces there. And then if I go to my milling tab, select milling, select drilling there, and it goes right into the drilling operation. And if I go back to my features tab here real quickly, you can see that it also automatically creates my feature for me without using that actual hole recognition function. So that's a nice little feature there. And this works as well with pocketing and facing. So if you just want to select a face that a pocket is on, you can, or create a pocketing operation, what you can do is select the face and just hit pocket operation. And that will create the feature for you, and you just go right into creating the operation. Another great tool for within Esprit is going to be called our expression functions and using the expression builder. This is a tool that it's a really powerful function that in my experience, not a lot of customers are really utilizing well. The way it works is you can actually set up Esprit so that certain parameters within an operation get automatically filled in based on the data from the feature itself. And so I'm going to go ahead and give you an example of this. So I'm going to go back to Esprit here. So right now I have these hole features here, and I know that these hole features are 1/8" holes. Right now I don't have a tool in my file I don't have an 1/8" drill to drill those. What I can do is I can create an expression so that Esprit will automatically pull a drill that will actually work for those holes. So what I do is I right click on the tool ID here, and I'm going to click Edit Properties. And this brings up what's called the expression builder. And in the expression builder, there's a whole bunch of different tools that you can use to start building your expression. And the way the expression works is it says, okay, I want to, let's say, go to the KBM utilities here, and I'm going to get a drill tool. So here's my get drill tool expression. And the expression right now has a whole bunch of different options of how I can filter the tool that I want to look for. So I can look for a range of tool diameters. So I can define a lower tool diameter or an upper tool diameter. I can set it up to just match the tool diameter to match the feature diameter. You can filter by minimum flute length so that the drill has to be a minimum flute length to drill that hole, minimum tool length. So what I'm going to do right now is I'm going to go ahead and type in here feature dot diameter. So what it's going to do is it's going to analyze the feature diameter. It's going to recognize what that diameter is, and then it's going to look in my tooling database that I have created in Esprit, and it's going to pull a drill tool that matches that feature diameter. So right here is what's called the compile expression button, and what it's going to do is it's going to analyze this expression and see it should return a result for me. So I click the button, give it a second, and it says result equals drill of, it's an 1/8" drill. So I'll say okay. I'll say okay again here. And now my drill tool is updated to match the feature diameter. So once I go through my operation here and I put in a couple expressions, I'm going to do one here for grabbing the tool. I'm also going to create an expression for setting a PEC increment based on the tool size. I set these expressions and it'll pull that information. And then let's say I want to use this process file. If I save the process file and I want to use it on another feature, it'll actually update the tool to match the feature. So if my next feature that I apply the process file to is a 1/2 inch hole or a 3/4 inch hole, it'll actually pull in a 1/2 inch drill or 3/4 inch drill to match the feature, which is really nice. And so here you can see this is just the the expression builder. We just built one for feature dot diameter. I'm going to show you now one for doing a PEC increment. So right here, I have an expression, and I just have it in a text document. I'm just going to copy it over. So what this expression is doing is it's saying, okay, it's analyzing the tool diameter, and it says if my tool diameter is less than a 1/2 inch, then it's going to divide that tool diameter by 2 and use that as my PEC increment. And then if it is not less than or equal to a 1/2 inch, it's just going to use a 0.2 inch PEC increment. So if I go back to Esprit, cycle type, I'm going to change it to drilling with chip removal, which is our pecking cycle. Here's my PEC increment. I'll do the same thing. I'll go to edit properties. And right here, I'll just copy in that or paste in that expression. And so I used an 1/8 inch drill. So when I hit the compile expression, it results in a 1/16 inch PEC increment. I'll say okay, and I'll say okay, and you can see it updates that. And what you'll also notice is if I change my drill here, so if I go to this larger drill, this is I think a 1 inch and a 1 1/4 inch drill, and I go back, it now updates that PEC increment based on the new tool, which is a really nice function. I'll switch this back to the 1/8 inch drill. It goes back to my 1/16 inch PEC increment. And yeah, that's just an intro into expressions. We are doing a webinar next week on Thursday of next week at the same time that goes over some knowledge-based functions and it talks about expressions. So be sure to check that out. Okay. So another great function here is going to be called the hole feature function, and it's a way to kind of manipulate and control your hole features. So here you can add new holes to the end of the collection. You can insert new holes into already within the hole feature. You can delete holes. You can also manually move them around. And you can also control the hole properties of those holes. So I was talking about the expression builder looking at the feature for a lot of data, and this is like the data that it's looking for. So if I go back to the demo part, all I have to do is I double click on my hole feature here. Okay. Here is the current hole feature organization, and you can see all the different holes here. And I can drag and drop these if I wanted to move them around. I can also control the different data points that are input into the hole feature. So let's say I have a chamfer on these holes. I could input that there, the chamfer diameter and chamfer angle. And then I could use that in expression so that Esprit, let's say we're doing a spot drilling operation here. For the tool selection, I can say, hey, I want to grab a tool that matches the chamfer angle, and it would pull in the chamfer angle based on the angle that I input here. So you can see how this kind of works with the expressions to really help you reduce the time you're taking to program in Esprit and kind of automate things. We also have some hole reordering functions. So you can reorder by these categories here. There's also built-in ordering functions into the operation itself. So let me go back to Esprit real quickly. Cancel out of the hole editor. So if I click on this hole here, the drilling operation, on the general tab, you have machining order, and this is just a quick way to kind of control your machining order here. And one of the nice things as well is you'll notice that I have some holes that are on a flat surface here and then holes that are on a wrapped surface. It's all being controlled within one operation. So it'll actually drill the wrapped holes first and then move over to the flats, which is really nice. So I can go ahead and simulate. Let me input a feed rate for my operation here. And if doing that peck operation for the wrap tool. And then it's going to rotate over and do my other holes. And I can control the order that those holes would get drilled in there. All right. So we also have some other, you can sort one other way, and I'll actually go through that real quickly. So hole reordering, you can do a couple different options here. You can reorder your holes by doing a zigzag pattern, whether it's vertically or horizontally. You can do it by coordinate along the x-axis or y-axis, and you can also do it by length, just whatever the shortest path is to take. And I can give you an example of that right now. Go ahead and open up a new file here. All right. So here I just have a hole feature, and it has all of these little holes right here. I'll go ahead and double click on that to bring up my hole editor here. And if I click on the overall hole, the one that encompasses all of the individual holes, I have my sorting routine here. You can do a manual sort where you can drag and drop, which is really nice. You can also do by length. You can do a zigzag order and change it from vertical or horizontal. And you can also do by coordinate here. So X, Y. So right now it's along the X, and you can switch it to order along the Y. There's also spiral. If you have them in a circular pattern as well, it'll do like a spiral move. But that is the hole reordering functions. Next, I'm going to talk about the drilling cycle enhancements. There have been a lot of improvements with the drilling cycle over the years. Here are a few of them in regards to stock automation, rotary machining, some of the new cycle types that have been added and improved, and then also custom cycle drilling, which is a really cool feature. All right, so Esprit is constantly analyzing and updating the stock, and it's using that information to sort of improve or optimize the tool path. What I mean by this is in this operation here, if I'm creating a drilling operation, and let's say I've already spiral milled a counter bore, Esprit recognizes that. And so I can use this use previous stock setting to define the starting depth of my hole. So what it'll do is it'll use that already counterbored material. It knows that material has been removed, and it'll define the starting depth within that counterbore so that it's not just feeding down that counterbore. It kind of removes a little bit of some of the feed. Rotary machining is also another great improvement. It's now just within operations, so you have a rotary machining option within your drilling operation or your pocketing or contouring operation. And you can control pretty easily whether you want to use a rotary axis or not. So I'll go ahead and bring this file up. Give it a second to load here. Okay, so in this file, you can see I'm going to focus right now just on this hole pattern along the top face here. So right now I have an operation here to drill all of those holes already. And if I open up the operation on the general page here, rotary machining, it's set to no. I'm going to hit OK, and I'm going to go ahead and simulate this really quickly. If I hit play, you can see what it's going to do is it's going to drive the tool around without using any rotary axis because I told it not to. However, if I do want to use the rotary axis, I'll go back into the operation, go to the strategy section here, rotary machining. I'll set it to yes. I also get this option now for position angle. Where do I want to do the drilling at is essentially what it's asking me, at what rotary position. It is in reference to the positive x-axis. So at position 0, it's going to be on the right side of the part here. Let's say I want to drill maybe just keep the tool at the back side of the part and drill at that position there. I'll input a 90-degree angle here. say okay. And now if I simulate, what we should see is drilling and just rotating that rotary axis, keeping the tool in the same position. It's along Y0 and drilling those holes. So again, setting up your rotary axis is really easy, and just defining whether you want to use it or not is just literally an option that is yes or no in the operation. There's no separate operation for using your rotary axis now. Okay, here are some of the new cycle types. So right now in Esprit, in the drilling operation, there's a strategy page and there's a drop down, and you'll be met with this this image here, and it lists all of the different cycle types. Some of the ones that I'm going to be talking about are going to be drilling with chip braking, bore with feed retract, and I'm going to be talking about the custom cycle here. There's a lot of improvements with support for boring now. So bore with feed retract is a good one, bore with rapid retract. Back boring is now fully supported, and we'll just take a quick look at that, what that looks like in the drilling operation. Precision boring is also a great improvement. It allows you to put a shift on for your boring operations. But yeah, we can go ahead and start taking a look at some of these cycles here. So I will go back to my Esprit file. Actually, let's see, first one. So drilling with chip braking, this is a new cycle. And what it does is just a partial retract move to really break that chip. It doesn't actually leave the hole itself. It's just a small retract move. In Esprit, when you're defining this, you'll set it to drilling with chip braking, set your pecking mode, and then set all of your different pecking increments. So right here, I have an operation already set up for us. Take a look at that. Again, just on the whole page, we have drilling with chip braking, set your pecking mode, and then all of your pecking increments. And we can just take a look at this in simulation. Let me go ahead and grab that operation. What you can see are these small moves that are breaking. It's just a small retract move, but it's used to break that chip. So that's just a defined cycle that comes with Esprit. Next, I'm going to talk about boring with feed retract, and this is just a boring cycle that's going to use a feed move to retract out of the part. You can define your feed move out of the part as a percentage of the defined feed rate. So if we go into the cycle here, you can see set it to bore with feed retract. You can set all of these boring cycles as cam cycles if your machine has the capability. And then you can set a dwell for once it gets to the final depth, dwell before it retracts. And then this retract for feed rate percentage is basically, you can set it as a percentage of the defined feed rate. So whatever you set the operation feed rate, you can say, okay, I want to retract at maybe 200% of that defined feed rate. So it's still a feed move, but it's a little bit faster than what you were actually boring at. And we can take a look at this inside of Esprit. So here's my boring with feed retract function or operation. And here's my tool. See, it's a nice boring tool. And I'm going to go ahead and step through. So now you can see it's rotating. We get that full profile. And now it's feeding down. Gets to the final depth, and now it's doing a feed retract move back out. So again, just another supported cycle within Esprit. Now I'm going to just go back into the boring cycle here, and I'm going to show you a couple of the other boring cycles. So back boring here was another great improvement. Again, you select back boring, define your shift distance and your spindle orientation angle, and it kind of controls all of those factors for you within the operation. So that's another nice one. Boring with manual extract will output a stop code once it gets to the bottom so that you could then manually extract the boring tool if needed. And then precision boring allows you to apply that shift distance as well and apply a spindle orientation angle. So these are just some of the boring cycles that are included with Esprit. So this is another great improvement. It's a new cycle type. It's called custom, and it basically gives you complete control about what's happening within your drilling cycle. So when you set your drilling cycle type to custom, you're going to get this menu here, and you could then input all of the different moves that are happening, and you can really have control. And this is built into the software, so when you post out, it's going to do exactly what you see here, exactly how you're controlling it. And so I'll go into Esprit. I'm going to go ahead and cancel here. And right here, I have, so I'm pilot drilling all of these, these outer holes here. I'm just going to focus on this one though. So first we pilot drill, and then what we're going to do is a deep hole drill or a gun drill. So I'll go ahead and open up my gun drilling operation here. My cycle type is set to custom. And right here, I'll just go ahead and kind of start this over so you can see how it works. Essentially, it'll be blank if you're starting fresh. And right here, so first thing we want to do is, let's say so this is going to be a deep hole drilling cycle. What I'm going to do is I'm going to select, first move is going to be a feed move. This is a metric file, so I'm just going to say 2,500 here, millimeters per minute. We'll go down to a depth of 25 millimeters, so about an inch. And that's going to be the first move. Then I'm going to come in here. Once we reach that depth, what I want to do is I want to ramp up my spindle speed. So it starts with the defined on the general tab here. It's going to start with this initial RPM and feed rate. And then once I have this spindle speed here, let's ramp that up to maybe 5,000 RPM. So we'll go to 5,000. And then we'll do a dwell. So I put in a dwell here. And we'll say 2 seconds. That allows the spindle to get up to speed. And then we'll kick our coolant on. So coolant will come on. We'll do on through spindle. And then we can do another feed move down. We'll use the same feed rate, but this time we'll go down to a depth of, yeah, maybe 75 millimeters. Once we reach that final depth, what I'll do is let's reduce the RPM back down to maybe like 2,000. We can do another dwell just so that it has time to reduce that feed rate. We'll turn the coolant off. So I'm turning the coolant off here. And then we can just feed back out to maybe 2 millimeters above the hole. And that'll be my just example for a deep drilling cycle. I can say okay. Then I'll go ahead and simulate it. Okay. So first thing I'm going to be looking down here. So I'm going to step through this. First thing that happens, we kick onto that initial RPM and feed rate. Gets down to depth, and then it kicks up to 5,000 RPM, and then goes to the next final depth, still at 5,000. One more step. It reduces that feed rate now, kills the coolant, does a dwell, and then it retracts up to 2 millimeters above the hole. So just like how I was doing, how I defined in that operation, you can see that's what it's doing here, and then the posted code will match that as well. So again, those custom drilling cycles are really a great improvement, and that's a really cool tool that I'm pretty impressed with. Really happy about that one. Spiral milling is another, there's some great improvements. So until now, it wasn't possible to apply a spiraling cycle on holes having different directions. We've improved the cycle so that holes with features that have holes with different directions are now supported all within one operation. And the transition between the holes adopts the same links technology used in drilling cycles. So we can just take a look at that. I'm going to switch back to that original file here. I had a spiraling operation in that one. So here you can see I have a spiraling operation that's going to do these two outer pockets there, and then this one here. And if I go ahead and simulate this, so it does the first one. I'll turn the feed rate up. Retracts, rotates, does the second one. Now what we're seeing here is it's going to retract to a safe position to index this B-axis head. And this is just how I have the operation defined. And I'll speed this up. And now it comes in and does that different orientation spiral operation. And that's all within one operation, which is really nice. So that's a great improvement to spiral milling. And another improvement with Esprit is our new coolant options. So we are fully supporting machine-specific coolant definitions. There's full support for high pressure coolant, and then also you can adjust coolant per operation now, which is really nice. So what you see here is when we are creating these machine files, this is a view of part of the MPRJ, which is a machine project file. We get documentation from OEM suppliers and OEM manufacturers, and we use that documentation to essentially match our machines in Esprit to what the OEMs are providing. And that way we can provide you guys with our digital twin. I know you guys hear that a lot, but we really are working and striving to provide digital twins, and this is one way that we are doing it. So we are fully supporting machine-specific coolant options now, which is really great. I was also talking about coolant options for within the actual operation. So you can define it in the tool still, but then if you also want to define different coolant options by an operation basis, you can do that now. So you just turn on this coolant override, select the coolant type you want. You can define the pressure that you want to use and if your machine is capable, an exact pressure value that you want to use, which is really nice. And so that is my presentation. I'm going to go ahead and pass it over to Jim, and he's going to talk to you about some drilling theory and some considerations to take into account when you're doing drilling operations. Thanks.
Thank you, Kevin. Hopefully everyone's doing okay today, and thank you for being in attendance. Hopefully I'm showing the full screen. And so again, my name is Jim Nielsen. I'm the round tool specialist with Sandvik Coromant. Been doing drilling for many years. Coming to you live from Huntsville, Alabama today. So we're going to talk a little bit about theory, process considerations, how to apply, maybe a little bit more deeper in depth on deep hole drilling, and then highlight a new product that was just launched back in April. So we'll get into it. We're going to talk in theory. We're going to look a little bit of terms and definitions, touch on calculations, and a little bit about the drill design. So when we're drilling, of course, first thing we got to look at is what type of holes. There's all types of holes. There's holes for clearance. There's screw heads, countersunk holes, holes with tight tolerance that need to be reamed. Maybe some heat exchanger type holes. So we really need to approach it and look what type of hole we're going to be producing, what kind of tolerance is required, what kind of depth is involved. So that's kind of one of the first things we look at when we Kevin, can you hear me?
Yeah, I can hear you, Jim. Yep.
Is everything okay?
I only see a black screen right now. You might have to switch to the presentation screen.
Okay. Tell me.
It's still looking like the notes screen.
I'm sorry, people. I'm trying to. Well, Kevin, I am struggling trying to get it to the screen. I don't see that option on here.
Okay. So do you have in the webinar menu that drop down under the play button for screen?
People can see your screens. Click to stop sharing.
Yeah, I would say, the notes screen will work, I think, if you want to just continue on with the notes.
Okay, I apologize. So again, we've got to identify the type of hole. So what we go by is we follow the ISO 13399 standard, which everyone is kind of adapting to. So we're all speaking the same language when we talk about different features or different envelope dimensions of a drill. Whether it's overall, we all call it LF, or flute length, which would be the LCF or LU. So when we're looking at drilling, lengths of the drill is critical. The flute length, which Kevin mentioned earlier, is critical. But what you want to take into account is really the LU. If I have a 1/4 inch drill and the flute length is 2 inches, let's say, it doesn't mean you can drill 2 inches deep. You've got to account for chip evacuation. So the way everything is given is in a LU, which is your usable length. So typically it's you subtract 2 times the diameter of the drill. So your usable length on a 1/4 inch drill with a 2 inch flute is somewhere around 1.5 inches. So that's something to keep in mind. Points on drills, when we look at a point, there is the different features of a drill. So whether it's the chisel in the center, the very center of a drill doesn't cut, it displaces material. And then you come up the primary and secondary cutting edges, which creates your chip. And then the chip is evacuated through the flute. And the drill diameter is supported by the margin or the land, as shown here in this screen, to support the drill in the hole. But if you didn't have that margin and it was full cylindrical, you would create heat and rubbing. And then very, very critical is selecting the right speeds and feeds, whether it's your RPM based on your surface foot recommendation. So you got VCs, your cutting speed, your feed per rev is FN, your VF is your inches per minute, and everything's based off your drill diameter. So when you look at at one of our books or one of our guides, they're going to give you a recommended surface footage. So you got to be able to convert that from surface feet into RPM based on that drill diameter, and then go with the recommended feed rate based on the material you're cutting. So we always recommend to go to the Core Plus tool guide. It can help guide you through tool selection and also define those speeds and feeds for you. Another thing to keep in mind is tool deflection or drill deflection. So you always, rule of thumb, always use the shortest drill possible. If you're drilling, 2 to 3 times D, you don't want to pull out a 5 or 8 times D drill, even though you can do it. It's just for every, if you go from a 2 times D to a 4 times D drill, you're increasing your tool deflection by a factor of 8. So the longer you go, the more deflection, the more run out possible, the less tool life, less, the hole quality may drop. So you really want to keep in mind to always try to select the shortest drill possible for the application. Another thing that's good to know is the design and the manufacturing tolerances. So at Sandvik Coromant, which as many drill suppliers, we tolerance our drills to an M7 tolerance, the diameter. So it's a plus tolerance. So it's really important to know that. So if you're trying to hold a certain size and you go, oh, I want a 1/4 inch drill, well, just know that 1/4 inch drill is going to come in at 2502 to 2506. So you most likely will be able to hold somewhere around a 251 to 252 hole size, as long as you're running it in a good holder, spindle, fixture, collet, and so on. And then all the shanks are tolerance to an small h6, which accommodates for shrink fit or hydraulic holding, so that you get proper clamping. So it's important to understand the drill tolerancing. And then geometry. The geometries nowadays that we're coming out with, we don't recommend using spot drills or starter drills, or in most cases, because the drill points are self-centering. They have good centering properties, and you really don't ever want to follow. If you use a 90 spot to create a chamfer, you might want to think about reversing and drilling first, then coming back in and putting that 90 spot after to break that corner, or combining that tool into one. Because what happens if you come into that hole into a 90 or a 120 or a 60, whatever it might be, you're, instead of hitting on the point first, you're hitting out at the outer corners, which then creates excessive wear, chipping, and your tool life drops. Also, different point designs, drill designs. We have different points for steel, different points with corner breaks for cutting cast iron, more of a brad type point for aluminum. So on breakthrough, you get minimal breakthrough burrs. So there's all kinds of things we can do to drill points and geometry to optimize it for the cutting. As well as if you are, drilling or drilling chamfering, drilling counterboring, we have a tailor-made option where we can either design a tool that fits your need, and so it's all a one shot, and we also do offer the drill and some drill chamfers to that correspond with tap drill sizes. So you already have a drill chamfer tool that corresponds with tap drill sizes that is available. So once we kind of know a little about the drill, and now we got to analyze, right? We're looking at our component. What's the shape, the size? How is it being held, clamping? Is there any reaches involved? Do we need any kind of extensions? So you really got to understand and analyze the component that's going to be machined. Material, no question. It's going to be one of the first questions you're asked is what are you drilling? What's the hardness? What's the condition? So it's very important to understand the material, the condition, and the hardness to be able to select the proper drill. And then diameter. Are you trying to hold a tight diameter? Do we need to ream? Are we going to a deep hole, as Kevin mentioned earlier, where we got to utilize deep hole drilling process? And then what kind of hole quality? What kind of finish requirements are involved? So part of that considerations is also the machine. What condition is the machine in? On lathes, how's the alignment? Drilling on a lathe, that's one of the biggest issues we see is alignment. So always make sure that the machine's aligned. The minimal runout, on these carbide drills, end mills, whatnot, we want 5/10 or less. 2/10 is ideal, a runout. Do we have adequate chip evacuation? Are you going to need a pecking cycle, or do you have through the tool coolant to be able to evacuate chips? So those are all things you need to think about and understand. And then when you do start talking coolant, what are the influences of coolant when you're drilling? Well, of course, if we're going fairly deep or beyond anything beyond 2 times the diameter is consider, you really want to start thinking coolant through the drill if the machine and everything's capable. So it aids in chip evacuation, aids in hole quality, tool life. Make sure you're running the right amount of concentration on the coolant. So those are some things to think about. Also, it's always a preferred method through the tool coolant to avoid chip jamming. That's going to be your number one. Really, one of the biggest and number one issues with drill breakage is chip evacuation. You either need to peck or you got to get chip out of the hole, and if you don't, you're going to break a drill and you're going to break it quick. So always is recommended at 3 times or beyond 3 times if possible. Coolant flow, this is just a good rule of thumb, no downward drop. So if you turn that coolant on, you're looking at the drill, you want to make sure that coolant's staying strong and straight for at least a foot, 11, 12 inches. If you start seeing any downward drop, you might not have good pressure, good flow. So in this, we'll kind of build on what Kevin talked about, the deep hole drilling process. We have drills that are designed for this. It's our 861 family. They range anywhere from a 12 times, 15, 20, and 30 times D capabilities. All these drills, we recommend the GP or the pilot, so a starter drill. And what the starter drill does, it's built to work in conjunction with the deep hole drill. The pilot drill has a different point angle, so it's going to be, let's say, 150 included, and then the drill that follows is a 140, so you're hitting at the center, not out at the corners. Also, I had mentioned earlier the M7 diameter tolerance. Well, on the pilot drill, it's got a P7, so it's a slightly larger size, so it acts more as a slip fit guide versus any kind of interference or rubbing. So you really want to utilize a pilot and then the deep hole. And when you do that, we'll take a closer look at the strategy. The pilot drill is going to come in at the recommended speeds and feeds, and you're going to drill a minimum of 1.5 times the diameter of the drill. You can go 2, you can go 3, but a minimum of 1.5. You're going to bring that longer drill in at a slower RPM with the coolant off. And some people ask why the coolant off. Well, one of the main reasons is if the coolant turns on at the wrong time, you can get a little kick or a little whip. And if that happens at the wrong time as the drill's entering the hole, you could grab a corner or chip a corner. Once we get in with the long drill and get down close to where the pilot left off, we're going to bring our RPM up to 100%, hit our feed, at 100%, cool it on first, of course, and then let it drill to depth. There's no reason to, as long as you have proper coolant, which here's 20 bar or 300 PSI or beyond. We want to make sure we're looking at 3, 5, or 1,000 PSI ideally to help with chip evacuation. Once you've drilled to depth, you're going to slow the tool down, retract, and you can retract at a faster rate, 2 or 3 times the drill rate. Of course, you can play with that to minimize cycle time losses, and then turning the coolant off. Now we'll just show a little video showing the same animation, showing the actual process with the deep hole drilling with the pilot. The deep hole drill has double margins, which again helps guide the tool as you get down and for straightness. So here your pilot's drilled your 1.5, 2 times. Long drill enters, coolant on, feed and speed up to 100%, drill to depth, retract, slow rate, and now that's completed the cycle. So if we follow the strategy, usually it does a very good job. Same kind of strategy, but now we have we're going into an angled surface. Well, when drilling an angled surface, you really need to create some kind of a flat or a spotting point. So you're going to use an end mill, helical interpolate, because you don't want to just plunge straight down with an end mill in most cases, because you still leave a little nib in the center. So ideal, you want a helical or come across the part and create that flat, and then you're going to follow the same strategy. Remember, utilize the Core Plus tool guide for speeds and feeds and tool selection. Now, besides, we talked about the deep hole drill, but when you look at the drill offering, it's unbelievable. We have, the deep hole drill, which we just talked about, double margin. We have micro drills that, go down to about 1/16 of an inch with coolant through the tool. So in that case, you're thinking about filtration. You got to have really good filtration so you don't get any kind of junk or dirt to plug a hole in those type drills. We have drills that are specific for steel, for stainless, for aluminum, for ISO-S, for nickels and titanium. So we really, have the full gamut of tools based on your application. So But what I mentioned earlier is we introduced a new drill back in April. It's the new 860 GM, and it's the one shown here with the coated tip. And this is a great, if you don't know, what to select, or you're in a shop or something, you're doing multiple materials. One day it's steel, stainless, aluminum. This is a great multi-material drill. And I'll run the animation on this just to give you a little more information. Again, multiple applications, tip coated, and so that gives you the wear and the tool life that you're looking for, and heat resistance at the tip. But it utilizes a new flute form with a high polish, so chips flow better over the polished surface versus a coated surface. So you get better chip flow, less tool pressure. The corner utilizes a little small corner break, so it protects that corner from damage or chipping. The thinning is more of a radius, so you get better chip flow into the flute and up and out of the flute, the polished flute. The edge prep, which kind of pre-breaks in the cutting edge, along with the edge reinforcement on the margin. This tool, double margin, great for going through cross holes and, exiting on angled holes. It gives you great support. So if you're really looking for a drill that can really do a lot or almost do it all, the 860 GM is really an item you would want to take a look at. So thank you. And Kevin, you can take it back.
Yep. All right. Dan, you want to go ahead and close this off here?
Sure. So we'll go through some Q&A here at the end, but before we do, I just wanted to remind everybody that part 3 of this series, which is innovative turning techniques, is going to be 2 weeks from today. So same time, 2 weeks from today, we're going to primarily be talking about our profit turning cycle, which greatly reduces cycle time and increases tool life. And then we'll also discuss some grooving methods as well. And then Sandvik will be there for this one to talk about their latest tooling advancements that coincide with those topics. So just to go through a few of the more commonly asked questions that transpired during the session, I guess we'll start at the top of the list here. So one of the users had a question about the orientation of the P-top features or the holes on a model, and whether or not different holes at different orientations could be consolidated into one hole feature. And the answer is yes. That's one of the topics that Kevin talked about in the beginning. There's a checkbox in the hole recognition dialog for having a hole to be machined at the active work coordinate. So if you want to recognize a hole at the active work coordinate, you would leave that box checked. And if you want Esprit to pick up the holes at different orientations, you would simply uncheck that box. So I'm gonna, there's a couple Sandvik questions here. One for Freddie. One of the attendees is asking if the pilot drill should have the same angle as the deep hole drill.
Freddie, I can take that.
Yeah. Yes. Sure.
Yeah, I think I mentioned that, or our pilot drills, we have a different point angle. So we have a flatter 150 on the pilot and a steeper 140 on the deep hole, so that the deep hole drill that follows the pilot hits in the center versus the outer corners and helps it center better and track straighter, if that answers the question.
Okay, so some of the users were asking about some of the different functionality that Kevin was showing. There was a question about whether or not the expressions would work in an older version of Esprit, and the answer is yes. I mean, I don't know if we would go back really far, but this question was about Esprit 2018, and I can confirm that the expressions he showed will work in Esprit 2018. This session is being recorded, so we'll be sending that out to everyone, and you can get the expressions out of the video, or we'd be happy to email them to you as well. So as far as another Sandvik question goes, Jeff was asking if there are any rules of thumb when selecting solid, indexable, or replaceable tip drills.
Jim, you want this one or do you want me to take it?
Well, I mean, my thought is solids. You know, when you get 5/8 and below, 1/2 inch and below, and then once you start hitting that 1/2 inch, 5/8 diameter, then replaceable heads and indexable start coming into play. Freddie, do you agree?
I do, along with the tolerancing required to the hole.
Yeah,
Whether
definitely.
or not,
Yeah, definitely carbide's going to have a tighter tolerance hole than an indexable and better
Mhm.
finish.
Yes.
Okay. So several of the attendees were also asking about where to download the latest version of Esprit, and it's available in the Esprit downloads on our website. But if you want to email support@dptechnology.com, we can send you a link and get you started with the new version of Esprit. When you make that request, it's also best to specify which machines you'd like to program with the new version, just so that we can make sure that they're available for you in your downloads and customer files. So Stephen had another question for Sandvik on the deep hole drilling. When drilling through a part, should a parameter be adjusted for the pressure drop?
I'll let Jim take that one.
Well,
I'm assuming he's referring to the coolant pressure.
Yeah, so it sounds like at the end of a deep hole drilling cycle, but like right before you drill through a
Break out.
part, should you drop the pressure down?
no,
The
there's
feed.
no need to on breakthrough to drop the pressure. The only time is if sometimes you hit an intersecting hole and you don't drop the pressure, but you change your feed rate as you go across. So if you're drilling in one side and then you're hitting a hole in the middle and going back into the other side, you're gonna drop your feed rate across that hole and into the other side and then bring it back up. But coolant pressure can stay at 100%.
Yeah.
Okay. So one of the attendees was saying that they didn't see the new coolant option available in the version of Esprit that they were using. So that could just be a matter of updating the machine. Since this is new functionality, it's possible that the machine they're using just needs to be updated, and that's something that our support team can handle. So if you just email support@dptechnology.com and specify the machine you're using, we'll take care of that for you. So there's one other Sandvik question here. It says, after the dwell at the bottom of a drill, can we stop the tool, reverse the tool on the way back up to prevent tool wear?
My response is no to that. I'd like to confirm that with Jim too, though.
Yeah, I've not seen that have any favorable effect
No.
as far as reversing the rotation of the drill. No. I mean, one thing I would point out is when you are pecking in the peck cycle, we don't ever recommend to fully retract if you don't have to. If you can retract to a point that you clear the chips and then go back down. So fully retract pecking just gives the opportunity to wear the corners quicker as you keep entering the hole. So when pecking, try not to fully retract if you're clearing the chips okay. You may have to fully retract if you're not, but if you can help it, try to stay within the hole on your pecks.
Yeah.
Okay, and that can be done with the drilling cycle, the chip breaking cycle that Kevin was showing earlier. You can achieve that method that Jim was talking about. So I think we hit all the more commonly asked questions. If there's any remaining, we'll follow up individually. And just want to remind everyone that next week we do have our knowledge base webinar, during which we'll go into a little bit more detail about things like expressions and program automation in general. And then, like I said earlier, 2 weeks from today is the final part of this series, which is focused on turning. So thank you everybody for joining, and we hope to see you in the next sessions.